Hi, I hope you guys looked at all these beautiful volcanic video clips that I presented the links from. And it's been a while. I've been very busy, so I've not been able to record many of these lectures. But today I'm doing it. I had a lot of change in my life. My son got married. The beautiful little lady that he met on the internet. And so we had a wedding party here. And I got 10 people or so in spite of COVID here over the floor. And we had a party. Now, I'm first going to take these stupid things off. I mean, every self-respecting YouTuber or local video guy shows these things. And I got perfectly good microphone on my laptop, so I don't need it really. But the wedding party was an excuse. I mean, we don't drink a lot of alcohol in our house, and except for here and there, a nice little brandy nightcap, which I love. But most of the time we drinking fizzy water or something like that. So I decided, with such a large crowd in the house, maybe this is a time to experiment and buy a soda stream machine so we can fizz up the water. And guess what we put in the fizz? Yeah, CO2. And then I thought of, hey, what if we're doing an experiment on the video for geology for engineers? And that's what we're going to do now. Ha ha ha. Because we have here 2 bottles of soda water. Right. This one here is warm. It's room temperature. And this one is cold. I use water from the fridge and then fizzed it up with the soda machine. So the question is, which one holds more fizz or more CO2? The warmer one or the cold one? So we're opening the warm one. Did you hear the fizz? Not that loud, but it was there. And then pouring it in my speaker's lubricant glass. And then, can you see it? Yeah, there is some fizz in it. Definitely. But it's a little bit. It's pretty cold. So, it's not that cold, I mean. So it's not that refreshing. And here is the colder bottle. Did you hear that? That was quite a bit louder. It was more pressured up and it contained more CO2. And I put it in my speaker's lubricant glass. You see the fizz? A lot stronger. It holds more CO2. And remember our introductory videos where we were talking about the solubility of CO2 in seawater, and that the warmer it gets, the less CO2 can be contained or dissolved in it. And the colder the water, the more CO2 it contains. So if you're coming out of an ice age, the ocean water can contain a lot of CO2. A lot of this CO2 is dissolved in the cold seawater. But when it warms up, more and more CO2 gets released from solution, from the seawater, and it escapes into the atmosphere. So that's one of the arguments why you say that CO2 follows the temperature curve. If it gets warmer, there's more CO2 in your atmosphere. So that's a little bit opposite what you learn every day in the newspapers. Santé. But that's not the topic today. We're talking about igneous rocks and how to classify them. And we have magma, the rock melt that is entrapped, intruded into the crust. And we have lava, the stuff that flows out over the surface of our planet, on top of the crust or on the bottom of the ocean. When a melt cools off, right, then minerals crystallize from this chemical concoction that we call magma or lava. And when it gets colder and colder, more and more material will crystallize out. And that succession of crystallization, which is also, of course, dependent on the chemical composition of the melt, changes with pressure and temperature. And we call this, in scientific terms, the thermodynamic phase diagram. Ha! Here we have a very simple phase diagram of water. Water is a single mineral, and it can occur as a gas, water vapor, liquid, water, solid, ice. So here we have the phase diagram of water, and on the vertical axis we see the pressure, so the changes of water with increasing pressure. Oh, I have to get my pointer. Pressure is low here and high there. And then we have on the horizontal axis here the temperature going from low to high temperature. It gets warmer to the right. And you can see already, right, that here, this is strange. This is where we're going. This line represents where we're going from ice into water. And if the pressure increase, you can see that ice start to melt at lower and lower temperatures. Hey, isn't that a bit strange and unexpected? Okay. Now, when we deal with rock, right, or a melt intruded into a crust, then it occurs at a certain depth and that depth doesn't change. So the pressure of the overlying rock column exerted on the melt is more or less stable. Unless the depth of burial changes, the pressure doesn't change. But over time that melt will cool off. So the pressure is constant, and the melt crystallization, or the crystals that form out of the melt, are mostly a function of temperature. So if you have water at one temperature change and a constant pressure, right, and you go from warm to colder, you go from gas to liquid water to ice. And the same happens, but in a more complex pattern, when you deal with a rock melt, because that is a mixture of all kinds of minerals that have been dissolved or molten into the melt and come out whenever the composition, for that composition, the mineral at a certain temperature is scheduled to come out. right? So those phase diagrams are a little bit more complex. Here we're dealing with igneous rock classifications. So we're talking about classifying rock that either is recrystallized in the crust due to mostly falling temperatures, or molten rock that recrystallizes at the surface when the temperature of the lava cools off. And the first way that we're classifying it is based on the texture of the resulting rock. Get it? So typically we can have phaneritic and aphanitic rocks. And phaneritic means only that the crystal size is pretty coarse. It's a large crystal size. You can easily see with the unhelped eye, the unaided eye, the crystals. And that indicates that you had pretty slow cooling. Also, if you have different minerals, then you can get some crystal size variation. So a phaneritic rock typically has a relatively moderate variation because mostly the slow cooling. If you have very little variation in mineral content, then it can become even acrigranular, right? All the same type of grains or crystals, I should say. If you have aphanitic or fine crystalline materials, then that indicates a rapid cooling of the melt. So you get fine crystals, or if it is extremely fast cooling, you get something like volcanic glass, right? Obsidian, vitreous or amorphic means that when you can see through the crystal, through the rock, it's basically amorph, then that indicates extreme fast cooling. Then we can have porphyritic rocks, with larger crystals floating in a fine ground mass. Now, this stuff is a little bit strange, but the large crystals are the ones that come out first out of the melt, right? They crystallize first, and therefore they are called firstlings or phenocrysts, and they floating in a mass of much finer crystalline materials. And that ground mass embedding all the large phenocrysts can be phaneritic, coarse, or aphanitic, very fine crystalline. And then finally, we have fragmental rocks. And this is mostly volcanic ash and bombs and other exploded rock fragments, right, that fall to the earth, and there they get amalgamated, glued together or molten together due to the temperature of the material, and we call that a fragmental rock. So you can see that texture is already an indicator from where how the rock was formed. A phaneritic rock, slow cooling, is often inside the crust. It's a plutonic rock. Aphanitic, very fine grained crystals, means that the cooling was fast, like happens on the surface of the crust in a volcanic setting or on the bottom of the ocean. Then we can have a porphyritic ground mass rock with phenocrysts, firstlings, very coarse, and then embedded in a ground mass that can be phaneritic, coarse crystalline, like Pluton, formed in a plutonic setting, and aphanitic or volcanic glass, like when it was formed in a volcanic setting. Oh! And then if you have pyroclastic rocks, like ashes and volcanic bombs that were all dumped together and they were spewed out in the atmosphere and then fell back to the earth, and they can amalgamate, get glued together and form a fragmental rock. And that's mostly pyroclastic, right? That's volcanic ashes and bombs. And then also we have pegmatites, which is a very late in the cooling process formed plutonic rock. It's still underground, in the surface, intrusive, often found in cracks and veins. And they have an often very large, coarse crystalline texture. Okay, it's the final crystallization of the magma in the crust. Wow. So here we're going back to the phase diagram. And remember, we have this textural classification, but also we have a classification based on rock composition. And the composition of the minerals is determined by something called the Bowen series. That's the product of the phase diagram that we showed you earlier, where the pressure is stable and then the temperature changes continuously. So first come out of the melt, crystallizing the very dark colored minerals, the mafic minerals, such as olivine, pyroxene, hornblende, and biotite. They're high in base metals, they're high in gold, high in silver, high in iron, lead, tin, all that stuff. They're dark colored minerals. And then we have the light colored minerals, felsic minerals we call them. They are the muscovites, the alkali feldspars, such as orthoclase, which is often radioactive, or with very typical twinning under the microscope, you can see that, of plagioclase. And then finally quartz comes out. And here you see a graphical presentation of this Bowen series, right? With the highest temperatures here at the top of the thermometer, and then the lowest temperatures here at the bottom. And then there's of course also a role of melt composition that plays a role. But typically we get first the dark minerals, the base metals, crystallizing out as minerals. The darkest is called ultramafic. Then we get the mafic, and then we get intermediate colored rocks. And then the light colored minerals become felsic. They are called felsic. At the highest temperatures, we get olivine, pyroxene, and then lower amphibole, and then ultimately biotite coming out. And then also the plagioclase series here, going from orthoanorthite to oligoclase. Sorry, it's been a while. They come out at pretty high temperatures simultaneously with the dark metals. And then the rest of the light colored minerals, orthoclase, muscovite, and quartz come out last. Those are the residual phases, last to crystallize, right? And it's just a reflection of the phase diagram. What comes out of the melt of this very complex rock mixture, this mineral or chemical mixture, right? This chemical cauldron of poisonous materials, a witch's brew, and it contains so much that we get all those different minerals coming out depending on the temperature and to some degree the composition of the melt. So when you have a rock that is high in silica, high in quartz, silicic we call that, it is typically acidic. And if you have a lot of base metals in there, like magnesium or lead or gold, right, then become dark colored, mafic, and they're called basic rocks. And so we classify acidic rocks as having more than 66 weight% of silica in the rock. And if something is intermediate, then we have 52 to 66 weight% silica in it. And basic, it's kind of grayish color, I would say, is 42 to 52 weight% of silica. And ultra basic is 45 weight% of silica. And then there are also a series of rocks that are light colored but have absolutely no quartz in it, and those are called feldspathoids or phuoids. Right? We'll talk about that in a second. And then we have acidic rocks, right, that are typically felsic, high in light minerals, and then we have basic or ultra basic rocks that are often dark and mafic in composition. So now you get a little bit of feeling for what is going on and how to classify these rocks. But there is more. I mentioned some rocks are light colored but do not contain quartz, zero quartz. It's an igneous rock that is undersaturated in silica. And those light colored rocks are not called feldspars, but feldspathoids or phuoids. And examples of that are minerals such as neveline, leucite, sodalite, and gancrinite. I've never seen them in real life, but that's what they are. So we're going to talk about plutonic classifications here, right? That is magma intruded in the crust. And you can see here a photo. Here's a photo around Ray Lake in Nevada. And I mean, here is an entire magma cooled off and crystallized and then brought to the surface and weathered and eroded. And the mountains are formed by the erosional process where the softer materials typically get eroded out easier, and thus this landscape is sculpted. That's not the shape of the Pluton, as we call this thing. It's the result of erosion. This might be just a bulbous accumulation of rock that then later was sculpted out by erosional processes. And this is the Sierra Nevada Pluton. So there you see one at the surface. Going back to the phase diagrams and so on, and here you have the feldspars, right, with the oligoclases, the K-spars, and the plagioclases, which is a mixture of silicates, silica-rich minerals, where we go from 100% calcite to 100% sodium, right? And then here the mixture goes from 100% sodium to 100% potassium, or 0 sodium and 100% potassium, sodium. So the plagioclases are containing calcium to sodium, and the orthoclases are going from potassium to sodium, right? Geologists like to show everything in ternary diagrams, and they can show 3 components in this case: calcite, sodium, and potassium, right? Okay, we get there. So when we classify igneous rocks, in particular plutonic rocks, then we use these compositional diagrams. And I have to tell you here a story, otherwise it gets too boring, I think. And that is that we geologists, right, are not always that certain as to what we see. And so we're trying to bluff our way through it. And this happened to me as a young student when we went on a field school in the Eifel area in Germany, which is volcanic, in the Ruhrgebiet, if you know that term better, where they make Riesling wines. Yummy, yummy. Oh, something. And there, ladies and gentlemen, I was on this field trip, and this student leader, a PhD student, who was supposed to tell us what we could see, showed me this black rock, and he said, "This is obviously a monzonite," or something like that. I'm not quite sure what the rock was that he showed me, but it was just a black, shiny rock, and I couldn't see it then, and I felt such an imbecile, because according to the student field trip leader, this was obviously monzonite or whatever rock it actually was. And I said, I don't know, but how do you know that this is monzonite? How do you know this mineral so well? And then he had to admit, well, so-and-so told me after he looked through the microscope and identified the minerals. Oh, and you were bluffing me that you could see what was in there. You have to watch out with the geological critters, because they tend to do that. They want to show how good they are, and then they blurt something out without any true evidence there. Watch out for these guys. But here we need, in this type of classification, which is two ternary diagrams, two triangles on top of each other, right? And we're going from quartz 100% to 0%, and then in the absence of quartz, we get another light mineral, the phoids, right? The nephelines that we talked about, and the leucites, right? And then on the other corners, we have alkali feldspars, 100% here and 0% there, and 0% and 100% plagioclase, right? The calcium, sodium rich feldspars. The alkali or the potassium ones here, they are mostly radioactive. That plays a major role when you do log analysis. I will talk about that much later. Okay, so this is 0 quartz and 100% quartz. This is in the corner 100% plagioclase, and on this axis, the opposing side of the triangle, it is 0. So 0 alkali feldspars, 100%. And on this side, it's 0 plagioclase, and on the opposing corner, it's 100% plagioclase. You get it? So now, when you have those black rocks that we were talking about, you can't see anything. So how can you see in the field what the composition of these rocks is? Well, it has first of all to be a phaneritic rock. It has to be coarse crystalline, otherwise you can't see a damn. And then it needs to contain 10% of those light-colored minerals, quartz, feldspar, and feldspathoids. And then they have to be, as we call them, renormalized, so that they are expressed as quartz plus feldspar plus feldspathoids being 100%, right? Then you can say, okay, if it is 100% quartz, then we're dealing with a quartzolite. And if we have alkali feldspars or orthoclases, and it's 100%, then we deal with cyanide, or more precisely, an alkali cyanide, or an alkali feldspar cyanide. If you have a little bit less alkali plagioclase, still dominant though in it, we call it a plain cyanide. And if we have some more plagioclase in there, we call it monzonite, and then monzodiorite, and then a diorite gabbro. That is how we classified it, Granite is somewhere here, right? We have 20 to 60% quartz in it, and then it is on the dominant side, right, of the alkali feldspar. It can have both alkali and plagioclase in it, but alkali is typically, the orthoclases, as we call them, is typically granite. If it is more dominant in plagioclases, then we call it granodiorites. Get the drift? That is how we do it. And I think this session has lasted now nearly half an hour, and we're going to stop and we're creating another video for the remainder. Stop.